Last seminar this semester, it's our extraordinary seminar. We're so happy and lucky to have our speaker today, who essentially was attracted to Heart Rhythm Society conference, and I was able to convince him, twisting his arms, to stop in St. Louis on his way back to Germany. I'm really happy to introduce our visitor, our speaker today, Professor Philipp Sasse, who's from Germany. So he received his medical education from University of Cologne and was licensed as a medical doctor in 2004. And then he went on to conduct research at the University of Bonn, where he studied, and his doctoral thesis was on intracellular calcium oscillations, a potential pacemaking mechanism, early embryonic heart cells. And then he essentially transitioned as a faculty, junior faculty appointment at the University of Bonn, where he was really the first to design and create a mouse which showed a proof of principle that you can create a mammalian model of optogenetic pacing, and hopefully in the future optogenetic defibrillation. And then he went on and is now developing essentially new steps in optogenetics. Namely, he went through from already traditional use of various channel rhodopsins to use already optically sensitive signaling molecules, which can be essentially used to dissect how intracellular signaling is involved in various processes, in this case related to heart failure, hypertrophy, arrhythmiogenesis. And he will present today to us very interesting data, I hope, on G-protein coupled receptors, how they become controlled by light. And I'm really excited about this field, and hope we can develop a really fruitful collaboration in the future. And I'm so sorry that attendance is so low, but this is because essentially end of the year. Welcome.
All right, thank you, Igor, for this kind introduction. Thanks for having me here. My talk is today on optogenetics and induced pluripotent stem cells as novel approaches for the diagnostic and treatment of cardiomyocytes. I will start, or I will have my talk a little bit divided into, for the students, into the two main topics of cardiac arrhythmia, which are bradycardic arrhythmia or tachycardic arrhythmia. Cardiac arrhythmia, you all know, can be due to sick sinus syndrome, sinoatrial block type 3, or atrioventricular block 3. Classically, these are treated by electric pacemakers in patients. We all know that electric stimulation of muscle goes back quite late. First done by Luigi Galvani with his famous copper zinc arc, although Igor referenced much earlier from other people. And I found it fascinating that Walter watched him develop the battery by looking at this local element. So basically, the development of battery is a physiological experiment before that. You're all aware that when you use electrical stimulation in the cell culture dish, that this makes pH changes, electrolysis, and changing of ions. It's also not very uniform, because you always have virtual anodes and virtual cathodes in a two-dimensional tissue, even if you stimulate with a field stimulation. And you always obviously do not have selective cell-specific stimulation, or never are able to really have continuous prolonged stimulation with electrical currents. So we thought about using an optogenetic approach by using channel rhodopsin 2, which is a classical non-selective ion channel used in the field of neuroscience. It opens up with illumination with blue light and then conducts ions, thereby leading to depolarization. And actually it's found in green algae in the areas where it's cloned from. We took the chicken beta-actin promoter to drive channel rhodopsin expression with EYFP, generated mouse embryonic stem cells from this construct. You can nicely appreciate the membrane-bound EYFP fluorescence as a sign of membrane-bound channel rhodopsin expression, and these then used to generate transgenic mouse in the cell culture dish, or to generate transgenic mouse cardiomyocytes in the cell culture dish and transgenic mouse for in vivo analysis. Here's a video of such cardiomyocytes in the cell culture dish. You can nicely appreciate several individual regions, spontaneous beating, individually, non-coupled, and whenever we flash blue light into the preparation, indicated by the blue box, you can see synchronous activity. This can be done over minutes, hours, or even days without a real drop down. The fascinating new thing is that right now we can also have a continuous illumination. Prolonged illumination increases spontaneous frequency because we just depolarize the pacemaking cells slightly a little bit, and thereby letting them reach the threshold potential earlier. We extensively characterize these expression proteins in cardiomyocytes from cells. You see nicely the non-bound fluorescence signal in single cardiomyocytes, light-induced invert current, and light-induced free-running action potentials in the current plasma. You can also appreciate that prolonged action potential, prolonged illumination leads to prolonged action potential duration to a potential maybe of about minus 40 millivolts. We'll come back to that in a second. If we then plate purified cardiomyocytes on such microelectrode arrays that can be used to generate activation maps, you appreciate that when we flash blue light to this region, activity starts here, from red is early and blue is late. When we flash illumination to this area, activity starts here, from red early, blue late. Quite obviously, and obviously could have also be done by moving of a single electrode. If we look at the calcium transients, we see that this is normal calcium transient in black. We can see that the tail calcium transient is prolonged when we prolong flash illumination. So the recording here only starts after termination of illumination, and prolonged illumination also leads for prolonged calcium transients, and we're currently using this to investigate excitation transcription coupling with prolonged action potentials by optical stimulation. We can generate a transgenic mouse that nicely express channel rhodopsin in the T-tubulus system and also in the cell membrane. In these isolated cells from these have nicely blue light-induced invert currents, free-running action potential by brief light flashes. And then we went on and did in vivo stimulation with intubated ventilated mice under a microscope for optical stimulation with a light-emitting diode. And this is, here you see a representative experiment. Below you see the ECG. You can appreciate here normal sinus movement without illumination with the P wave and the narrow QRS complex. Illumination to the left ventricle leads to a broad QRS complex, one-to-one coupling to the blue light intensity, indicating a ventricular pacing. Also illuminating the right atrium leads to supraventricular pacing, indicated by a one-to-one coupling of blue light flashes to the P wave and a broadening of the P wave, because we obviously that electric activity doesn't start in the sinus node, but just in the area where we flash illuminate to. We have used this method to look what is the lowest minimal area, and currently with our current setup, the lowest area is 250 micrometers in diameter, is still sufficient for ventricular pacing, and if you calculate that we should, a monolayer that is about 50 cells in that area, we currently use this to look at think-thoughts relationship in the ventricle by looking at different illumination sizes and the effect of pacing. And also something what is new, we can do prolonged illumination to the ventricular area, and we find that during this prolonged illumination we have nasty ventricular extrableeds, and we assume that it's coming from the border zone where we have slightly depolarized cells being pacemaker cells. There is absolutely no side effect of channel rhodopsin overexpression. This is important to know, since it could be leaky conductions that could induce modified resting potential, which it doesn't. It could affect membrane resistance, which it doesn't. It could affect action potential duration, no effect here, and also no cardiac hypertrophy we will observe in our transgenic mouse. To put forward an idea of clinical use, channel rhodopsin, we have used adeno-associated viruses driven from the where chicken beta-13 promoter drives channel rhodopsin, this time infusion with cherry. Inject these intravenously, and after 4 to 8 months we find vast expression of channel rhodopsin in the ventricular wall, in the ventricle, also in the atria. And if you look at the confocal microscope, you see good expression in the T-tubulus, similar to the transgenic mouse. And I have to say, this is 4 weeks, up to 8 months, even up to 8 months, it looks completely the same. So it's a very long-lasting expression, although it's episomal vector. And we assume that this is because cells just do not divide and the cells keep in the vector episomal state. When we now dissociate cardiomyocytes, we can see here as an overview image that maybe about 60% of the cardiomyocytes are generalizing positive. And here's an image of dissociated cells. You can nicely appreciate that blue light flash illumination leads to contraction of isolated ventricular myocytes after AV gets
question.
Yes.
So the one on top is not responsive, right? Yeah, this one.
Yeah, this one is just moved passively, but it is 60%, so this may be one of those 40%.
And do you get variability with your intravenous injection in the percent? Is it 60 is about the best, or is it?
Yeah, this may be 42, no, it's maybe 52 to 70, something like that. I mean, this is n equals 5, standard error of the mean, so it's around 60, and it's not so much variable. Also, if we look at the fluorescence intensity over time, I don't have the slide up there, then we do not see an effect of times in culture, times in vivo. Seems to be not affecting at all. At least there's no real correlation between the duration of the experiment and the intensity, fluorescence intensity. We had, out of 20 mice, I think we had 3 dropouts, but these dropouts could be explained by too low fluorescence. This is why we cannot simulate this with all the others, because this is a very robust system. And I'm almost completely surprised seeing this. It's something I didn't really expect. And these cells like induce invert currents as expected, and I produce free running action potentials. Then we went on and did the same epicardial illumination in vivo to look at stimulation thresholds. We always do 40 light pulses at different stimulation durations, and then determine what is the minimum light intensity for a one-to-one coupling. Quite long and stressful experiments for the investigator, because you have to tune with each stretch. You have to tune down the intensity until you don't see one-to-one coupling for all. So we find, by using this, we are able to do some strength duration curve, or classically we would say Cronach serial-based plots for neuronal excitation, and we find that low intensity, high intensity stimulation is required for 2 milliseconds long pulses, and if you increase the pulse duration to 20 or 50 milliseconds, we can lower the light intensity as required. And this is all true for 3.6 millimeter in diameter, 10 millimeter square in area. If you increase that area to a larger area, 25 millimeter, you can even lower the stimulation threshold. And we find it interesting to look with that method to look at the sync-cross relationship, because it seems to be not so important how much milliwatt per square millimeter you apply to the preparation, but more or less how much millimeter you apply to any area. So it seems to act really as a sensitium, integrating all the light on all the current and in one sensitium. This works for up to 10 minutes, as long as we have tried so far, but after 10 minutes we see that the QRS shape looks very similar. Termination of the illumination with a little pause, sinus rhythm is restored without any problem. And during the 10 minutes, there's even not a single dropout of beating. So this is beating rate 80 beats per minute pace, and you see no dropout. To put forward the clinical idea of stimulation with a light-emitting catheter, we inserted a light guide into the left ventricle, in this case in lung preparation. You can appreciate that you see the illumination from the epicard, and that is able to stimulate also from that area. Now we need how much higher light intensities. Here we are sitting at maybe 6 for 2 milliseconds, 6 milliwatt per square millimeter, and because the area is just smaller risk of light. Optogenetic stimulation also works with skeletal and smooth muscle cells. Here is an example of the expression in our transgenic mouse model, in the soleus muscle, where light-induced contraction, asymmetric force measurements, and we're currently using this to make optogenetic opening of the vocal cords. You might know that the posterior muscle is the only muscle opening the vocal cords, and it's very difficult for electrical stimulation because the recurrent nerve always innervates also the anterior and lateral muscles. And with optogenic stimulation, we are nicely able to selectively illuminate the posterior wall of the expanded larynx, and you can see in the video that this nicely opens the vocal cords, so you can look down into the trachea And we think that this could be a new potential method of treating bilateral paralysis, where electrical stimulation really doesn't work very good in patients being done, but it's not with therapeutic options. And this might be a new option for these patients. Optogenetic stimulation, this is just a brief, I have nothing to do with cardiac stuff, also here is a brief outlook. You see that there's nice expression in the smooth muscle cell of the aorta, and blue light illumination, induced contraction, and asymmetric force measurements of aortic rates in a similar range than norepinephrine induced contraction. Not only for a minute or two, but even up to 10 minutes or even longer. And we currently use that to look at the interplay between member potential and ligands in smooth muscle and also intracellular cells. Yes?
How many cell layers deep can the light penetrate? Because when you're opening the vocal cords, what cell layer do you have to activate? Or is it just the surface cell layer?
No, because we know that that by increasing the light intensity, we can increase the strength even in the soleus muscle. And since this is a all or nothing response, we believe that by increasing light intensity, we must reach deeper layers. And this fact tells us that it's not a surface layer. However, if we look at tachynos contraction, we are maybe getting 80% of the force that can be induced by electrical stimulation. So we do not activate all fibers in the skeletal muscle, but at least in the soleus, this is maybe 2 or 3 millimeters in diameter of the mouth. I think maybe 80% of the fibers we can activate.
So ideally, you want this to activate in the atrium, not the ventricle, but it looked really patchy in the atrium, your expression.
Yeah. We don't know if this will ever work. And so you're right, the atrial expression of the using the adenoacetate viruses, it works patchy here. It's looked even worse after 8 months, to be honest. So we can stimulate atrial. I only showed ventricle here because atrial stimulation is not very consistent. Ventricle always works. Atrial is not very consistent, and we need high light energies. So we don't know if AAV9 is the best type for infecting atrial cells.
Right.
Yeah.
Is part of the heterogeneity also within the cell, so at the cellular level, or is it when the cell expresses it everywhere
Yes.
throughout the T-tubule system and the membranes?
When the cell expresses, it's expressed everywhere. So there's no heterogeneity between cells. There's between cells, but not within one cell. Okay. So far, this is everything I would like to tell you on member potential induced optogenetic for looking at member potential. The next part, I will spend a little time on intracellular signaling cascade. You're all aware of the GQ signaling cascade, which is mainly involved in smooth muscle contraction, but also involved in cardiac pacemaking, especially in embryonic cardiomyocytes, involved in arrhythmia in pathological states, and also in cardiac development. And it works that GQ activates phospholipase C, producing IP3, which then releases calcium from IgG-sensitive calcium stores. Also the GS signaling cascade, which is quite obviously everybody knows, it's one of the most important signaling cascades for the heart, involved in cardiac pacemaking, intracellular arrhythmia, and also activated too long induces cardiac hypertrophy. And we thought about if it could be possible to use optogenetic methods to stimulate these systems selectively, because with classical methods you have either cell-specific stimulation, temporal specificity is quite difficult to achieve, and also local specific stimulation cannot really be done by organisms in vitro and also in vivo. And would then provide high spatial temporal resolution and be cell type specific. So for optogenetic stimulation of the GQ signaling cascade, we took advantage of melanopsin, which is expressed in our retinal ganglion cells in the eye, involved in day-night cycle, involved in melatonin expression. This is why it is called melanopsin, and maybe also involved in the fact that I'm still jet-lagged after a week being in the States. We took a construct with a chicken beta-3 promoter expression melanopsin, and together with the GFP verified the construct in 293 cells, which where light induces IP3 production, measured by the degradation product, IP1. Then generated mouse embryo stem cells with nice membrane-bound melanopsin expression. Again, cardiomyocytes in a culture dish. You can appreciate here in the video spontaneous beating of the coupled area. And when we illuminate the thing, you see now it just beat faster. This can be done repetitively. You see the blue light simulation by the blue bars here. This is the frequency analysis by infrared video microscopy to not activate the cell just by the imaging light. You can appreciate that the intensity or the frequency response is always quite similar. To show that it's really selective and not some unselective, unspecific effect, we block the phospholipase C, which induces, just focus here on the graph, induces attenuation of the light-induced frequency acceleration. Same is true if you block the pulse and release channel and the trip channels to APB, that also attenuates light-induced frequency acceleration. This can be also seen nicely in the statistics. Because melanopsin here is expressed under the chicken beta-10 promoter, it could possibly be true that non-cardiomyocytes activate by illumination, thereby producing hormone transmitters like norepinephrine and then paracrine. In effect, is inducing the frequency acceleration. To exclude this, we look just at single cardiomyocytes that nicely express melanopsin, and also in single cardiomyocytes we see light-induced frequency acceleration. So it's a direct effect and not an effect of paracrine.
However, if you affect this signaling pathway in non-cardiomyocytes, that over a prolonged period of time may have consequences for physiology as well.
Yes, it would be interesting to look over prolonged time what is going on with gene expression, and we are currently doing that. Yes, but
it'd be hard to tease out which cell type is going on.
Yes, absolutely. So this is why for the prolonged expression and for prolonged illumination, we're trying to get purified cardiomyocytes to not mix up with, or just embryonic stem cell differentiation. We know that this is a lot of different cell types, and we need to figure out later what that is the important cell type. Nice thing about this tool is right now, because it's so reproducible and so consistent, we can apply increasing light intensities, thereby doing dose response relationship. And this is a big advantage among all the other classic receptor pharmacology, where you just add doses, add, and you never know if a receptor desensitization occurs. And here nice, because we can, by switching off the light, we know the signal is off, and then we can, just using different light intensities, and always look at the response coming from the baseline. If we a little closer look at a couple of light intensities that we have applied, you appreciate that with high light intensity we have a fast peak in frequency, and then it's desensitization to a plateau level of frequency, and after termination of the illumination we go back to a baseline. And with low light intensity, for instance 40 nanowatt per square meter, we don't have a clear peak but more or less a plateau. And this is not a mistake. This is not milliwatt per square millimeter like for channelrhodopsin. It's truly nanowatt per square millimeter. So we are sitting here about 100,000 times more light sensitivity. If you plot in the peak frequency against the logarithmic light intensity, similar to how we would do it for receptor pharmacology, you can nicely appreciate a sigmoidal response, similar as with no-G protein receptor pharmacology. And with the EE50, which we call IC50 for light, about 37 nanowatt per square millimeter. And again, this is 100,000 times lower than what you need for channelrhodopsin. Also, time to peak is highly dependent on the light intensity, as you would expect. Faster peak is reached with higher light intensities, and vice versa. Interestingly, we observe after high light intensity stimulation of our GQ protein, in this black box or gray box, you can see that we see a non-regular beating. It can be much nicer seen, much more nice seen if we now have a so-called ECG plot where every line represents a single beat, and you see large pauses, fast acceleration of frequency, and then again pauses. If we, to statistically analyze this, we plot this coefficient of variation of the time period of the interbeat intervals after termination of illumination. We call it arrhythmia index. And we see that the arrhythmia index is, with low light intensity, the arrhythmia index is at baseline. And then after high light intensity stimulation, we see an increase of arrhythmia. And there seems to be a clear-cut difference around 40 nanowatt per square millimeter. And this is quite interesting, and we never observe this arrhythmic beating when we are having the physiological agonist like endothelium 1. And we think that by using an overexpression system, melanoid seen here, you can take the maximum out of the system, getting maximum activation, thereby maybe, let's say, somehow simulate what would happen if you have receptor overexpression that occurs during pathological state. However, there might also be other explanations, and we currently cannot do if this is really a physiological thing or just a pathological overaction of VQ stimulation.
So what type of arrhythmias are it? Is it?
Let's say it's irregular beating. I wouldn't say because it's spontaneous activity. So it's somehow, we think it's a negative feedback on the pacemaker cell that leads to this uncontrolled, non-stable rhythm in the cell culture dish. But we cannot say that this is somehow, because of the culture dish, it's not like an injury. It's an influence on the pacemaker potential, pacemaker activity in the cell. Like I would call it a sixth sinus syndrome if I would translate that into a clinical situation, but it's obviously a cell culture dish.
And is this light intensity truly 3 orders of magnitude lower than what you previously showed us in terms of the milliwatt per millimeter
Yes.
square? And
Yes.
that's because of the construct, or?
It's because, obviously we don't know. It's this construct seems to have 5-fold higher order of magnitude, higher light sensitivity, and we think because it is a natural construct occurring in our retinal ganglion cell in the eye. Thereby it must be light sensitive. It's important for day-night cycle. So it doesn't make any sense having this protein being responsible only to milliwatt per square millimeter, which is much more than bright sunlight. So obviously melanoid C needs to be something that is really happening in the room. And this is why it is in this region. Maybe right now here we have like let's say 800 nano or maybe 500 nanowatt per square millimeter in the respective wavelengths currently in this room. So you can also imagine that it's a pain working with this because we need to be completely up. Okay, so I showed you the nice temporal profile and arrhythmia generation. Obviously, melanopsin can be also, any optogenetic approach can be also nice and used for looking at spatial properties. This is again a multi-electrode array recording where you can see red is early and blue is late, so spontaneous activity and the spontaneous beating preparation of cardiomyocytes comes from the left. Now we illuminate a certain area, we see a frequency acceleration, and then the activity comes from the illuminated area. That's, I would say, it's quite obviously, but it's also quite interesting that the minimum requirement in this preparation is just the level of IP3. That is to determine whether an area is a pacemaker's area or not, or at least elevating IP3 level can switch a non-pacemaking area to a pacemaker area. Okay, I would like to switch and show you that this is very recent data, very recent unpublished data, optogenetic simulation of the GS signaling cascade. As I said, it's an important signaling cascade, and to activate this, there's unfortunately not a protein in the human body or in mammalian cells that can be used, but jellyfish. Jellyfish starts its vision with a cyclic AMP mediated signaling cascade, and therefore we just took the jellyfish obscene from these features expressed behind the chicken beta-18 promoter together with EGFP, generating mouse embryonic cells, embryonic stem cells, that leads to cyclic AMP production upon illumination. And actually it's in similar range than phospholene-induced activation of the amyloid light cycles. Again, we differentiate cardiomyocytes, and you can appreciate the frequency, the blue light-induced frequency acceleration in these spontaneous beating cardiomyocytes from stem cells, and in the similar range than activation of the beta receptor with isoprenaline. We generated a transgenic mouse from these stem cells with good expression in the atrium, also in the ventricle. If you look at the histology, it's a nice expression on the cell surface membrane, not so much in the T-tubule system. Then if we illuminate constantly on the right atrium, we see that 100 millisecond light pulse leads with a 300 millisecond decay to acceleration of the spontaneous sinus rhythm because we just stimulated GS signaling cascade in this sinus node. And this can be also gradiated. We have not further analyzed that, but it can be nicely gradiated. We are now sitting at microwatt, not nanowatt per square millimeter, and we believe that is because there is slight attenuation of the light going through the atrial wall until it reaches the sinus node. But you can appreciate that with higher light densities we see faster responses in the spontaneous beating rate acceleration.
Have you tried the pace from another site besides the endogenous sinus node area, like the left atrium or somewhere else?
Yes, we have tried it with the left atrium, and there something really interesting happens. We see a little increase of frequency, maybe until here, but then we see spontaneous extra beats coming from the left atrium. So we think that the frequency acceleration that we see by illuminating the right atrial region is protecting for or against spontaneous supraventricular arrhythmia that otherwise would occur if you only have GS stimulation in a non-pacemaking area. And that's why we think that.
And what about other sites in the right atrium? Or do you think it's like, are you looking?
We have not looked so carefully because for looking at outside the right atrium, you have to cut out their right atrium because the sinus node is inside, so we always have.
But actually, did you try that? You cut out right atrium, but stimulate left and see what happens?
No. Yeah, to see whether it can modulate spontaneous pacemaking. We also have not looked at AV node. Also, if we do that, we see, I cannot see it here, we see a shortening of PQ interval. So it seems to be also activating the AV node. Haven't looked carefully done this. I mean, this is a couple of weeks old. Okay, in the first part, I've shown you optogenetic stimulation of the heart and other muscles, GQ and GS activation with optogenetic proteins. I would like then switch to the second part. You all know tachycardia can be due to either supraventricular tachycardia, atrial fibrillation, or flutter. Ventricular tachycardia can be explained after cardiac infarction, mutation of certain ion channels leading to longitudinal syndrome or CPVT. Side effect of drug can induce, or abnormal electrolytes can induce long QT syndrome or other cardiac arrhythmia. And I would like to tell you to some parts of what we are currently doing to analyze the mechanisms here. First of all, quite a long time ago, we found that after cardiac infarction in the mouse, and this is a cryoinfarction with serious red staining, the transmural function. If we then do electrophysiological investigation to look at the vulnerability with the octopolar 7 mouth catheter, then we see that a burst stimulation protocol and also extra beat stimulation protocol leads to ventricular tachycardia that is free running but self-terminating in mice. When we transplant GFP positive embryonic cardiomyocytes, just GFP just to be able to identify them, when we transplant cardiomyocytes that nicely engraft with the scar, and we see here, then we see that the incidence of ventricular tachycardia is not as high anymore. Actually, can be also in the statistics, 40% of control mice can be induced VTs, 100% of infarcted mice, but only 40% of infarcted mice with the transplantation of cardiomyocytes. If you look carefully at the histology, you can see that there's connexin 43 expression between the cardiomyocyte, but also between the host ventricle and the cardiomyocyte transplanted ones. And then there was the question to me whether there's really functional coupling. And I tried a lot with two-photon imaging, and I'm a strong non-believer that this will ever work in a beating heart, even with levistatin and all that stuff. So you cannot do two-photon imaging, at least in my hands, it doesn't work. So we have come up with another idea. There was an optogenetic approach. We took embryonic cardiomyocytes before transplantation, labeled them with an antivirus expression the calcium-sensitive fluorescent protein GCAM2, which is shown here in the crystal structure. And GCAM2 only fluorescent when calcium is present, and thereby we just have an intrinsic labeling of beating of the transplanted cell. We take these cells transplant and just look at the equifluorescence of the heart and together with the spontaneous ECG of the host myocardium. And here you see the video of transplanted cells within the infarction. You can see that with every second beat. Now, Now, with every second beat, fluorescence is increasing in the transplanted cell as a clear evidence for, in this case, 2-to-1 coupling of host myocardium to transplanted cells.
What is the source of the embryonic myocytes and what species are
It's mouse to mouse, same background. It's embryonic cardiomyocytes. This thing, or at least this project, has been completely recapitulated by the Murray group with human iPS cell derived not only on a guinea pig, not only the arrhythmia idea, but also the functional coupling. They have completely recapitulated there, and so using human iPS cell derived cardiomyocytes. This is why we thought it's quite nice, supports our idea of reducing the vulnerability by transplanting coupled cells. So this is one therapy to this ventricular tachycardia after cardiac infarction. Although we also thought, is optogenetic defibrillation a potential possible mechanism that can be used? And this comes from coming back to in vitro data on microelectrode arrays. If we illuminate a certain electrode in a monolayer on a microelectrode array, in this case electrode 57, you can see that electrical activity on that electrode is completely silenced during illumination. And this comes because I showed you before in the beginning we are sitting at minus 40 milliwatt, so we can have the cell in a refractory state by prolonged illumination. And then there was a question, can we do also optical defibrillation? And in fact we can. This is some traces from epicardial recordings, ECG, and endocardial recording with a cyber mouth catheter that we also use is in Langendorf, that we also use for still burst stimulation. And you can see that the burst stimulation induces a short, free-running VT that would, without defibrillation, maybe last until here. Mice do not have sustained VTs, at least wild-type mice. And by illumination, the epicardial surface, you can see that the illumination induces a termination of the ventricular tachycardia. N=1, only a couple of weeks old. So we are currently using this and further investigating not only the clinical application, but also the mechanisms of defibrillation that can be now investigated using this optogenetic approach.
Does it matter which electrode you illuminate, whether you get it?
Up here, we can only, so whatever electrode we illuminate, we see electrical silence. So on the electrode where we illuminate, we see an electrical silence. Yeah.
But it may not be sufficient to defibrillate.
For defibrillation, we know, that the size of, at least in this N=1 experiment, we know that the size matters. So when we have a small illumination area, we do not get defibrillation. There's a larger area, we get defibrillation. So what we are currently obviously trying to investigate, what is the pattern that you need for getting log of rotors and all that stuff. So is it only the size, is the pattern, how is fiber orientated important, and so on and so forth. Yeah?
So can you also induce arrhythmias with the optically and the number of bursts S1, S2? Because the area that you need is quite large, and so the excitable gap is smooth. So just interesting.
We have not tried S1, S2. We haven't tried S1, S2, and burst stimulation will not work because of the 20 milliseconds of delay candidate time of terminal RC.
But you can do cross-field optical stimulation, basically inducing wave this way and then just blocking field of view.
Yes, we could do this. We have thought about that, but we can only do that when we have our digital mirror device installed to really be able to dial into any random pattern of illumination that we just cannot do with our standard equifluorescence system that we have currently available. But the plan is having a DME attached here to really be able to dial any pattern you can think of, and then you can also think of which pattern, if there's a gradient, and other things you can potentially think of, can be then done on this house. Okay. So showed you optogenetic defibrillation is one potential principle, and believe that it's not only in tachycardia, but also ventricle, but also in atrial tachycardia. However, I have not shown this yet. And I showed you that connexin overexpressing cells protects arrhythmia. So coming to the final part, long QT syndrome and side effect of drugs. Long QT syndrome, the name obviously comes from a prolongation in the QT interval in ECG, which is due to an action potential prolongation in cardiomyocytes. That leads to eventually leads to start the point. Arrhythmia in patient that can be life-threatening, and if you look at the Kaplan-Meier curves, you can see that after 30 years, almost 80% of patients had a cardiac arrhythmia incidence, being longitude 1, 2, or 3. Longitude 1 and 2 are classical mutations of the IKS or IKR channels, or KBAC and HERB channel, in human mutation leading to a loss of function of potassium channel and thereby loss of vaporization. I'm especially interested in longitude 3, which is a gain of function mutation in the cardiac sodium channel, because of the most common longitude 3 is delta PQ mutation, where inactivation through this loop doesn't occur anymore, or so would in wild type cells. And this can lead to a reopening of the mutated sodium channel and therefore prolongation of action potential, especially at bradycardic situation. To look at these syndrome in vitro, we took advantage of induced pluripotent stem cells. That's a technology where you take somatic cells, either from skin biopsy or keratinocytes from the hair plug, overexpress with certain different technologies the transcription factors, OCT4, KLF, SOX2, and CMYC. Maybe CMYC can be left out. This is technology invented by Shinya Yamanaka in 2007. And then you can take induced pluripotent stem cells for in vitro differentiation into cardiomyocytes and do electrophysiological catchment analysis. And I participated in one of the earlier studies where we used only OCT4 for reprogramming, and my job was to characterize the cells, cardiomyocytes, then we can get one of these IPS cells. To look at the longitude syndrome, we took right now advantage of a mouse model from the Bradycardic group, where they have introduced the delta KPQ mutation I just mentioned being important in human into the mouse cardiac sodium channel. We took this mouse model, generated feeder cells, induced the pluripotency by the factors, and differentiating cardiomyocytes to characterize them. These are the stem cells. Look at cell culture, nice stem cells, mouse endostems, they should exactly look like this. It's beautiful. And they'll express SSEA1 as a stem cell marker on the surface membrane, and OCT4 in the nucleus as they should. If we inject these cells into skid mice, we get nasty teratoma that shows cells, both cell lines we have generated show after injecting cells from all germ lines, and this is a classical showing for in vitro teratome formation, in vitro differentiation of various. Also, if you look at gene expression, we can see that day 0 is always a stem cell state, day 14 is the differentiated state. You can see that upper differentiation, OCT4, and none of this downregulation as these cells should do, and all the important cardiac factors, including alpha MHC, sodium channel, HCM4, potassium channels, the calcium channel, and actin are increased during differentiation. And importantly, we do not see a difference between wild type and SCN5A mutant IPS cells. These cells differentiated into the cell culture dish into cells of all 3 germ layers, endothermal, mesodermal differentiation, and ectodermal differentiation. And important for me as cardiac electrophysiologist, they differentiate into beating cardiomyocytes, shown here in this video, for instance. When we characterize these cardiomyocytes, show the channel expression looks very similar between cardiomyocytes from both cell lines. Also, electrophysiological investigation shows very similar peak current densities of sodium channel, but is also known for this mutation, should not affect sodium channel maximum peak current. If you look at the sodium channel recovery from inactivation, which is the classical parameter that is involved by the delta KPQ mutation, you can see that the mutated cells have much faster recovery of sodium channel availability than the wild type, also seen in the time constant statistics. And this is very similar to the cardiomyocytes from the publication of Peter Carmody from the local T3 mouse, looking almost exactly identical. We also looked at the leak current, which is a classical affected by this mutation, and we see that there's a larger leak current in the mutated cell, very similar to the cardiomyocytes of the mouse model. We then looked at action potential duration, and we saw that at around 2 Hertz, not much big of a difference of action potential duration. But then if we pace at 0.5 Hertz, slower pacing rate, we can see a broadening of the QS complex. To be able to quantify that, it is very similar from the mouse now. To be able to quantify that, we plot for each individual cell the pacing period versus the corresponding action potential. Here's just 2 examples, and calculate the slope of this action potential restitution curve. And we can see that the slope is negative for wild-type cells, as expected or as known for mouse, but it's a positive slope for the mutated cell, and again, this is very similar to the mouse model. And also, if you pace very slow, we can see early after depolarization action potential in about 50% of mutated cell, but never in wild-type cell, and also something that can be seen in the action potentials from the mouse model. To further bring this to automatic, yes?
Do you think that that's purely an effect of the sodium current, or do you think it's influencing the calcium current, and that's why you're getting the EADs?
It's effect of the sodium channel. These are patch clamps, highly buffered. I don't think that much of calcium plays a role. But this is why I say it's EAD, not EAD. So I think it's an effect of the sodium channel. This is also the literature that's important. To have a potential automatic or semi-automatic method of analysis, purified cardiomyocytes are required for automatic analysis. I'll show you in case how you can use them. However, the classical clonal genetic modification is very time-consuming for many different patients and clones, so we came up with a different idea. We take our induced pluripotent stem cells, infect them with a lentivirus, where the alpha-MHC promoter drives promycin and GFP, and then the REX1 promoter drives neomycin. REX1 is a promoter that is active in stem cells. By neomycin selection, we can select for integrants, taking the whole bunch of integrants, so it's not a clonal analysis, but more or less a batch analysis. And after differentiation of the cardiomyocytes, we apply promycin, and only cardiomyocytes survive that procedure. And these purified cardiomyocytes then can be used for conventional patch clamp, gamma patch clamp, or microelectrode array analysis. Purification of cardiomyocytes with this construct works quite well. You see the expression of the construct in the differentiation. After purification, we get about 100%, 95, 90% of cells are cardiomyocytes. We did the same electrophysiological characterization I've shown you before. Maybe just focus here on an example slope, or here in the summary, we can see positive slope in mutated cell and negative slope in the restitution curve in wild-type cells. Also, action potential duration we observed, and we also did some pharmacological investigation, and we can see that mexicillin, the classical use-dependent sodium channel blockers, also provides the prolonged action potential and slow pacing rates.
Question: have you also used other ion channels to try to differentiate more between atrial versus conduction versus ventricular myocytes to see what, how purified within the cardiac myocyte population?
Yes. No, we have not. The alpha-MHC promoter is highly active in pacemaker cells and atrial cells. Mm-hmm. And we also think that's the reason why here the action potential is a little bit shorter than if you compare to the whole non-purified cardiomyocytes. Mm-hmm. So there might be an effect. Still, we see an effect on slow pacing rate induced action potential prolongation. But this is a big issue in the whole field of IPS-derived cardiomyocytes. Everybody wants pure ventricular cardiomyocytes. Nobody has achieved that so far. But obviously, that would be quite ideal. Also, maybe I'll show you in a bit, if you differentiate from the ventricular action potential and only classify looking at the cells with ventricular action potential with cells with non-ventricular action potential, we see that this effect is more pronounced in ventricular action potentials. Because if they are long, they can be prolonged much easier by reopting of the sodium channel.
And have you tried length and culture to differentiate? Like other people have said, you need 30 days.
For the mouse, it's not really necessary. I'll show you in a bit the human data. There we tried a longer differentiation to just get the sodium channels up, because it just takes long to get sodium channels there. But we do not see a specification onto ventricular myocytes after longer So there must be other protocols that would be very interesting to see which factors are really doing the ventricular specification. So far, nobody has really succeeded in this field. Since we have right now purified cardiomyocytes, we can not only do the classical patch clamp with an electrode, but also a planar patch clamp, which is a last tube with a small hole where cell encapsulation is pipetted in by the robot. You see the robot in our lab and sucked into the hole and doing automatically whole cells and doing patch clamp recording. We have set up quite complicated protocols for capturing these cells and for doing current time recording. It's quite special doing current time recording, which does the system. Usually people only record ion channels. And we have developed a protocol to find the automatic stimulation threshold for action potential generation, because everything should be automatized in this situation. If you do such analysis, you can appreciate maybe here, look focus on the muted cellular slow pacing rate, a broad QRS complex. If we then plot the APD90 for several cells, we can see that there is a difference in the slope, and also in the statistic we see a positive slope with the mutated cell and a negative slope with the wild type cell. It doesn't really match completely our manual patch data, but at least points in the right direction. And also sometimes we observe early after depolarizations, but not as bad nasty as shown in manual patch analysis. Very tricky thing. I'm happy to see that we can see this data, but I have to admit this is definitely not something that is a high throughput platform. At least not from induced pluripotent stem cell derived cardiomyocytes. It's very challenging. And finally, I would like to show you the longitude 3 issue, that cardiomyocytes can be also generated from induced pluripotent stem cells. We have used longitude 3 patient or gained IPS cell from a longitude 3 patient with a different STN5 mutation, the R1644H mutation, but obviously has a very similar phenotype. In the control patient, skin biopsy was done in Münster, including IPS cell generation characterization, and we differentiated the cardiomyocyte and looked at the electrophysiological phenotypes. If you look at the sodium channel, we see a larger sodium channel availability, but this, since it's two different clones, can be also clonal selective. And this is also a problem because you don't really know whether it could be also a differentiation state, because we know longer differentiation, more sodium channel, and so I wouldn't say that this is only due to the mutation, but probably can also due to the different maturation state. However, recovery from an activation, because it's very nice, it's intrinsic control itself, recovery from an activation cannot be explained by different maturation states, at least I think so. And if you look at there, you see a faster recovery from an activation indicated by a slower time constant in the mutated cell and in the cells from the control patient. If you look at action potential durations, we can see that in the control patient, we don't have much of action potential prolongation at slow pacing rates, so not much influence. If you look at the longitude 3 patient, we observe even at 0.2 Hertz stimulation, 0.5 seconds interval, we see a prolongation. And if we stimulate much slower, we see that this prolongation even further prolongs. This is action potential duration in control and longitude 3 patient, where you do not see much of a difference. However, if we only look at cells with a ventricular action potential shape, and this is exactly answering your question or coming to that topic, we'll see that now we have a significant difference and a significant prolongation of longitude. If we then plot the slope, the idea I've shown you before, to be cell independent, to look at the intracellular control, just look at frequency dependence, we can see a positive slope in longitude 3, all cells, but also much more pronounced if we look at the ventricle cardiomyocytes.
Could I ask you, what is that hyperpolarization?
We don't know. Maybe they have expressed calcium-sensitive potassium channels. We do not always see this. Is something that we do not always see. But I don't know the molecular entity, and we don't have really statistics on that. Maybe calcium-sensitive potassium channels. We are also taking part on bringing these ideas of using patient-specific IPS cells to the next level and having everything automatized from getting the skin biopsy, the IPS cells, and also the differentiation into brain and heart cells within the stem cell factory consortium. And our job there is to do the automatic differentiation and the scale up and scale out of cardiomyocytes. Should be fully automized, the reprogramming colony picking is automized, the expansion is scalable, and the differentiation should also be scalable. This is how the machine looks like. It's currently finalized building, a linear robot with different stations where different tasks can be performed, and we hope that we can get a second funding round. This is really a project already, can get a second funding round to have another 1 or 2 years working on here, and I hope I can present better experience next time or results next time. So currently we don't know whether this is really working for automatic differentiation of cardiomyocytes. But it's just to show you that this project is one. If you're interested, there's quite a good website on the stem cell factory. I think we are quite advanced compared to international collaborators. In the final couple of minutes, I would like to show you again an optogenetic project. I briefly mentioned some time ago that field potentials can be also recorded from microelectrodes array, and the field potential duration is the surrogate parameter of the actual potential duration. And I also briefly mentioned that depending on different long QT phenotypes, some of them die during exercise or get cardiac events during exercise, not Q1 for instance, and some of them, not Q3 for instance, when they sleep. So there's a highly frequency dependent intrinsic mechanism of the mutation, and it's quite well understood. However, on multi-electrode array, cells are very difficult to be stimulated. And so we came up with the idea, why not using channel rhodopsin to stimulate cardiomyocyte or microelectrode array? And it works quite good. Here's a nice video I show you, spontaneous beating, and then with every blue light flash illumination, you can see they follow a nice 1-to-1 beating. And this is quite low light intensity stimulation for 1 millisecond only. We need to apply here to this human iPS cell-derived cardiomyocyte. This was achieved by adeno-associated virus transduction. In our hand, it's much better than using a stable cell line. So there's really good viruses that we can use here for introducing optogenetic proteins. About 50% of cells express mCherry and thereby are transduced, and it is more than enough for optogenetic stimulation. If we look at spontaneous activity, as you would expect, the pacemaker sits somewhere and electrical activity is conducted along the microelectrode array. And this leads to a non-synchronous activation of electrodes, and therefore spatial averaging among all electrodes is not possible. You always have to pick 1 or 2 electrodes and do the analysis there. You cannot do spatial averaging because you have the traveling wave. If you, however, global optical stimulate, everything shoots at once because you have global stimulation. Now everything happens at once, and therefore you can do spatial averaging, just average all electrodes. And also the optical stimulation can be done at 1, 2, and even at 3 Hertz quite easily without much of a problem. We use this to characterize the frequency dependence of different ion channel blockers. Here I show you 2 IKR blockers, or Herc channel blockers, Soltolo and E4031. Here's the raw data for the Soltolo experiments at 1 Hertz pacing. You can see a broadening of the QRS complex, so of the field potential duration, not of the QT intervals, of the field potential duration, but not at 2 Hertz. No effect at 2 Hertz. This can be seen in statistics, prolongation at 1 Hertz, no prolongation at 2 or 2.5 Hertz. And same is true for E4031. We're currently testing all the other available drugs for different repolarization curves.
And if you look at the T wave of the field potential, so what do you take?
We take the peak of the T wave. So what we usually do, with some filtering algorithm, we take the first derivative and see where the first derivative crosses the 0 line. And it seems that this is much...
Initially you call it electrogram, right? So you have remote repolarization. So why choose to take then the positive flank of it? Just like in
it seemed to be more consistent among experiments taking the peak. We also tried to take the end, so looking at different algorithms, also the upstream slope, but the most nicely correlating effect and the most clear noise-free data we get when we take the peak. So we measure from the lowest peak to the peak of the T. Although, and the effects are so clear, so it doesn't really, it's not so really much of importance.
And maybe the edges with more different electronic environments. So
Yeah, but since these cells shoot all at once, we have a global illumination, we don't have conduction anymore. This is why if you have global illumination, everything shoots at once, you shouldn't have too much electrotonic effects.
you have cells that have both side cells, you have cells that only have on one side cells. So you have a difference. But I mean, maybe that difference is too small.
Different.
To
At least in our hands here, it seems to work nice to take. We also try to characterize sodium channel availability by looking at the maximum negative downstroke. So first derivative of this signal, measuring the maximum negative downstroke, and we observed that application of the sodium channel blocker quinidine for Longstadt, and among all frequencies at 1.5 and 2 Hertz. And also interestingly, we find slight effect of potassium channel blockers on that downstream velocity parameter, especially at 2 Hertz, something we do not really understand currently, why this is at 2 Hertz. So, but you can, at least you can see that some sodium channel blockage can be also seen with that, possible with that analysis. So in the second part, I've showed you disease-specific IPS cells with non-T syndrome, purification strategy for IPS cell cardiomyocytes, and another one I've introduced. And I showed you the optogenetic analysis of drug-induced longevity. I didn't have time to spend on the longevity 3 optogenetic analysis, and I showed you briefly what stem cell factor is. I would like to thank the people who have actually done the work. First of all, Tobias Bruegmann, a former medical student, now postdoc in the lab, who did all the general autopsy work. Daniel Malan did patch analysis for general autopsy and also a lot for the induced pluripotent stem cells. Chris Vogt does the IAV story. Henrik Lapp, the optogenetic microelectrode array. Philipp Nokofka did GS, and Thomas Bayer did GQ signaling pathway, and Stefan Friedrichs does all the IPS cell work together with Ivan Matuszek and Frank Holz. I'd like to thank the people at Bonn, collaborating partners, the people who gave agents, the funding agencies, and thank you for your attention. Very happy to take questions.
Questions, please. We had a good discussion.
Yes.
So one question I have is, so as we all know, optogenetics really came from neuroscience mostly, and we still essentially getting some of the opsins which were developed by Karl Deiserov and others trying to adopt in the cardiac field. But how do you see essentially merging the two approaches? There are so many models now in different neurons. So to study, for example, autonomic system. So are you planning to generate animals which will have opsins both in neuronal system and in cardiac system?
I think it will, yeah. I think it will. So I'm not currently planning this right away, but I think it will be an important tool to look at autonomic regulation. Because as you know, there are currently these cardiac spinal cord stimulators in place, which stimulate the not very selective stimulator, but trying to stimulate the sympathetic nerve system, also stimulating parasympathetic nerve system. So with optogenetic approaches, this could be much more selective if you have the correct targeting of your proteins and the correct targeting of your light sources. So it could be also an interesting approach, but having said this, you can also take opsins like melanopsin, jellyfish opsin, and we are also working on different opsins for targeting intracellular signaling cascades directly, so you don't have to use nerve cells. You can just target these guys to the sinus node and just having a selective modulation of the intracellular signaling cascades. But obviously this is also a nice tool to look at the interaction between cardiac and nerve cells.
Do you think that the hurdles for pacing from the atria with these opsins will eventually be overcome, or is there some limiting factor as far as you were mentioning that stimulation was causing, what was difficult in the atrium.
Yeah, but I don't think that's really, it's just something you have not carefully looked at. So, I think there will be a method also using adenoacetate virus. Maybe it must be different serotype, or maybe it must be repetitive injections on all these things that I think will overcome these I would say small problems quite easily. So I think atrial ablation shouldn't be big of a deal.
But maybe alternative solution is gene painting, because what Kevin Donahue found exactly opposite, that he had difficulties transfecting ventricles, but gene painting works really well in atria.
Yes, it's just so difficult to access the atrium in a lateral thoracotomy in mice. So for gene painting, it would be very difficult. Nicely, you can inject the ventricle, but the atrium is so hidden and deep. So I would always go for trying.
Mark Anderson did it.
But to be honest, that systemic approach is so surprisingly and so good and so transmural that I would also put a little bit more effort in that, because if you do not need an operation, it's a good thing, potentially.
So any more questions? Oh, thank you. So did you get permission?